All right, the next thing we're going to look at is the chemistry of solutions. So we've already kind of mentioned a few of these terms, so there'll be a little bit of looping back around, but we're going to start out today just talking about aqueous. And once again, you recall that term aqueous. Aqueous means it's something that's dissolved in water. Okay, so you'll see here some substances dissolve readily into other things. Sometimes they don't. All right, in any solution, there's going to be parts of the solution. And so the first thing we're going to talk about is the solvent. Okay, solvent is the dissolving medium. That means that is the substance that is doing the dissolving. And so, in general, now this isn't always the case, but usually the resulting solution usually ends up looking more like the solvent than the other thing, the solute. That's not always the case, but usually that's going to be the case. And then another thing that is a generalization is that usually the solvent is going to be the thing that is present in the greater quantity. Not always, but generally that is true. Okay, so the thing doing the dissolving is called the solvent. The other thing, the particles that are being dissolved are what are called the solute. So the solute is dissolved in the solvent and it makes a solution. The process of this is called solvation. We already kind of looked at the solvation. We looked at water molecules kind of tearing sodium chloride apart and keeping them in little solvation bubbles, right? Where all the sodium, the positive sodium ions are surrounded by the negative oxygen end of the water molecules, and likewise the negative chloride ions were surrounded by the positive hydrogen end of a water molecule. So that was solvation. Solvents and solutes, they can be gases, liquids, solids, they can be any combination of that. But like we've mentioned before, aqueous though means that water is going to be the solvent. That's going to be the thing dissolving the other substances. Substances that dissolve most readily in water include ionic and polar covalent compounds. So things that are ionic, so made of a metal and a non-metal cations and anions, those usually dissolve pretty well in water because of the fact that they have positive and negative ions on it. And since water molecules have those positive and negative ends, it gives them something they can attach to. Likewise, things that are covalent or molecular, where they're all nonmetals, if they have polar ends, so just like water, if it has a positive and a negative end, water will do a good job at dissolving those things as well. Things that water doesn't dissolve very well are going to be nonpolar solutes, so things that are evenly charged throughout. Water has a hard time grabbing a hold of. And why this is because water has, it's a very polar molecule, and its bent shape gives it those ends. Okay, and let's see, advance. And so there's an example, again, we already talked about sodium chloride and the solvation of it, where you notice here's the water molecules with the negative oxygen in, the positive hydrogen in, and so they align themselves in a very specific way. Nonpolar compounds typically don't dissolve in water. And so best example I can give you this is something that is like oily. Okay, you might have had oil or grease on your hands, and usually when something's dirty, the first thing you do to clean it off is get it wet. You put water on it. And usually water works. Water is a really good solvent. It's what's known as the universal solvent. It dissolves most things. But if you've ever had anything oily or greasy, it doesn't work real well. The water just beads up and rolls away. And the reason for this is oils are made of very generally long non-polar molecules, long chains of them. And since it doesn't have any positive or negative ends, water can't grab a hold of it. And so usually to dissolve things that are non-polar is that you will use something called a surfactant, something like soap. So, and you've realized if you get something oily or greasy on your hands, water won't wash it off. But if you get soap on there, the soap will. We'll talk about that in greater detail later. So anyway, here it's just demonstrating. Here it's showing like hexane. Hexane is a solvent, an organic solvent. It's usually a ring of 6 carbon atoms. But once again, because their shape and the difference in the electronegativity between the hydrogen and the carbon, they're not polar. They share electrons equally. Water doesn't dissolve it. Okay, so a few things we're going to talk about now is just some general properties of solution. And so we're going to start here looking at how solutions are formed. Okay, so first off, the rate at which a solute dissolves is called the dissolution rate. This dissolution rate depends upon the structure of the solute particles, so basically their size, and then basically also how fast they're moving. So the faster you can get those things moving and mixing together, the faster the solvent can dissolve them. And so some things you can do to kind of increase this is you can heat it up or agitating it or stirring it. Okay, so as you physically just move those particles around and give them places for the solvent to come in and spread them out, it'll do it in a much faster fashion. And so, I don't know if you guys have ever noticed, but if you're making tea and you have like sugar in it, or this goes the same with coffee, if you have it granulated, so where it's all in little cubes where it's all crushed up, it dissolves much faster than if you put in, like those 1 cubic centimeter, like the 1 centimeter on each side, like a sugar cube. And so they'll dissolve faster. One, if the tea is hot, or two, if you stir the tea. And so even looking at this, if you drink, just like iced tea, I don't know if you guys have ever noticed when they make iced tea, they don't make it cold. All right, they brew it usually in like a coffee pot. They use really hot water to dissolve all the tea out of the tea leaves, and so heat will do it. Agitating will help mix that stuff up and get it dissolving faster. And so here it's giving you just an example here. So think again, kinetic energy of the particles. So if it's cold, they're moving real slow. They don't mix real well. But if you heat them up, they're bouncing around faster. They're able to dissolve faster. Same thing, by just stirring it, it'll cause those particles to rearrange more quickly. Okay, so we're going to look at some solubility graphs here in a minute. And so I need to give you some of this terminology that's going to be used. So anyway, it's given us example if you add 36.2 grams of sodium chloride to 100 grams of water at 25 degrees Celsius, it says all the salt dissolves. However, if you add 1 more gram of salt, the extra one will never dissolve. Okay, and this is what is said to be saturated. So a saturated solution is one that holds the maximum amount of solute for a given quantity of solvent at constant temperature and pressure. The solubility of a substance is the amount of solute that dissolves in a given quantity in at a specific temperature and pressure. Okay, so solubility means that it can't dissolve anymore. So let me give you an example. All right. Maybe at some point when you were a kid, your family bought some breakfast cereal, some breakfast food, and they got you like regular Cheerios. Okay, that's probably the day you suspected, or I guess your suspicions were kind of given some weight or some evidence. Maybe your family doesn't like you, because if they liked you, they would buy you the Honey Nut Cheerios. I'm just teasing. So anyway, nah. So let's say whatever reason you got the regular Cheerios. Well, regular Cheerios, you can eat them. They don't taste real good. So you want to sprinkle some sugar on there, right? And so let's say you put your Cheerios in the bowl, you pour some milk over it, you sprinkle some sugar on the top. Okay, if you only put like a teaspoon of sugar on there and stir it up, that milk will dissolve all that sugar. Okay, but if you keep putting teaspoons of sugar in there, let's say you put like 3, 4, 5, 6, you'll get to a point where the milk will no longer dissolve all that sugar. And so you have reached what is called the saturation point, the point where it can no longer dissolve any more solute. And so what happens in any of the extra sugar that you put on there? Well, it just falls to the bottom. Okay, so you get what is called a saturated solution. Before that fact, it was unsaturated, meaning that it could hold more. You could scoop more sugar in there, and yeah, it'll dissolve it. But you'll get to a point where that milk will not hold any more any more sugar, and it just forms as that sweet, sweet, sugary sludge at the bottom of the bowl. And so anyway, this is just a review of that term solvation once again. So it's talking about the particles getting in there and able to dissolve part of the solute. Okay. And so here is where it's talking about saturation. So as solute ions enter the solution, the relative amounts change until you're at an equilibrium. That means you have an equal number of those solute particles going into solution and falling back out. Okay, so before the fact you have, so let's say, you put some salt in water or whatever, you can put sugar in milk. Okay, and so you have all the solid particles together and the liquid will start dissolving it. Okay, well, and it'll keep doing that until it reaches a point it can't hold anymore. But if you look at it, just at the atomic level, some of those sugar particles are still dissolving, but then others are precipitating back out. You reach this thing called equilibrium, where it is equal. You have the same number coming in and out of the solution. So what I'm going to do now is I'm going to show you a series of graphs that deal with solubility and temperature. Okay, and so a solubility curve is a graph of the solubility as a function of temperature. You can use a solubility curve to predict whether a given solution will be saturated, unsaturated, or supersaturated for a given temperature based upon the amount of solute dissolved in the solution. The solubility of most solid substances increases as the temperature of the solvent increases, but there are some examples, like here you have ytterbium sulfate, the solubility will actually decrease, but usually they increase. Okay, and so this is basically what we're looking at when we look at a solubility graph. All right, and so what you're going to notice here, along the x-axis here, it's talking about the temperature in degrees Celsius, so it's showing you temperatures increasing. And then along the y-axis, this is showing the solubility of different substances. And so this is in a unit of grams per 100 grams of water, the solvent. Believe it or not, the graph has to tell you the amount of the solvent present because that affects how much you can dissolve. Example, okay, if I want to dissolve salt in water, it matters if I have a cup of water, or I have a bathtub of water, or if I have an ocean of water. Those volumes have a different carrying capacity for that solute. So you need to know the quantity of solvent, and this is probably the most common unit you're going to see, but you should always look at the graph and read to see what unit the amount of solvent is listed as. Okay, so in this example, it's showing how many grams of the solute for every 100 grams of water. And so basically, if you look at this, it's going to have three parts. It's going to talk about, okay, so that line that it's showing, that's showing the saturation line. So that part that where the maximum amount of water, or excuse me, the maximum amount of the solute is dissolved in that volume of water at that given temperature. So notice as temperature changes, the amount of stuff you can dissolve changes. So anyway, anything that is below that line, so like in this example, it's graphed out a point here, that is said to be unsaturated. Okay, and we'll talk about unsaturated here in a second. I'll give you a definition. And then if anything happens to be above the line, that is said to be supersaturated. And this is another graph just showing you how solubility varies with temperature for different substances. And so you'll notice things like, for example, potassium nitrate, that top one. It has, you look at the slope of the line. So obviously as temperature goes up, the solubility goes up, and its slope is fairly steep. So that means it has a pretty dramatic increase in solubility as the temperature increases. It shows you a couple of other examples here, like the sodium chloride, for example. Notice it doesn't change much. Okay, so its slope is very low. It is positive, but man, not very. Okay, so salt solubility doesn't change a lot with temperature, and then very occasionally with solid things, like if you look at that bottom line, I think it's yellow, I can't tell, but ytterbium sulfate, notice that as it gets warmer, its solubility actually decreases, which is actually kind of different for solid things. Not so much with gases. We'll talk about gases later. Okay, and so what I want to show you guys right now is just some definitions for these terms, and then honestly what I'm going to do is just work through a few examples of these type of problems and show you really how to read a solubility graph and how you can make different inferences from the information listed. As always, when I give you something that's on this type of document, this is something you'll want to jot down because it will not be in the it won't be in the slide presentation that I give you. Okay, so first again, we're going to start out just with some basic terms here. So types of solutions, we've already kind of talked about unsaturated before, but basically that is a solution that has less solute than it can at a given temperature. That means it has the capacity to dissolve more. Okay, so there's still room for more of the dissolved solute. All right, so that is called unsaturated. And then the next one we already kind of mentioned a little bit, so that's unsaturated. The next one is said to be saturated. So a saturated solution is that one that is holding the maximum amount of dissolved solute that it can at a certain temperature and pressure. That means it cannot dissolve anymore. So if you put any more in it, it's just going to sit there. Okay, it's just going to, usually if you're dissolving like a solid into a liquid, the solid is just going to pile up on the bottom. Okay, it's not going to dissolve anymore unless you do the next thing. So notice it has a couple of caveats here. It says temperature and pressure, and for solids it's only going to be temperature, but if it were gases, pressure will also affect solubility, and we'll talk about that here in a bit. Okay, so anyway, the last part, so we have unsaturated and saturated. The last one is supersaturated. Okay, so anything that is supersaturated, it's basically a solution that is holding more than the maximum amount of dissolved solute that it can at a certain temperature and pressure. And so you might say, well, how can it hold more? Well, basically, in order to supersaturate a solution, what you do is you'll take it and you'll get it to where it's at its saturated point, and then what you'll do is you'll increase the temperature, you'll heat it up. And as you guys notice by looking at those graphs, usually when the temperature goes up, the amount of solute that can be dissolved increases. And so basically what you're doing is you're heating it up to a point where it will dissolve all of that solute. And then as long as you don't disturb it, if you just leave it alone and allow that solution to sit there, usually that dissolved solute will stay in solution. Now, if you agitate it, if you bump it, if you add a seed crystal, stir it, do anything to it, then usually what happens is that all that extra stuff will precipitate out. Okay. So anyway, so unsaturated, less than the maximum amount. Saturated is at the maximum amount. Supersaturated means that it's holding more than it should. It had to have been heated up and then allowed to cool down. So those are kind of the scenarios that we are looking at. Okay, what we're going to do here, I'm just going to kind of show you some different examples of how you can read solubility graphs and how you can, obtain information from this. So looking at this first picture, this first question, I guess it says, how many grams of sodium nitrate will be dissolved in 100 grams of 45-degree water? So because it's talking about 45-degree water, we're actually okay. Let me see here. Where is, I got like a highlighter. So because it's talking about 100-degree water, we can use this graph as is. We don't have to mess with it, okay? And so we're looking at sodium nitrate. So we're really looking at this thing right here, okay? And it wants to know how many grams of sodium nitrate can be dissolved in 45-degree water. So what we have to do is we have to look at the temperature. Well, 45 is going to be right between 40 and 50. And so he basically just read this graph and you see where it intersects. And so it looks like roughly it should be about 110 grams of sodium nitrate. Now, this is one of those examples where I said, usually the solvent is what is going to be present in the greater quantity. Well, sodium nitrate is really soluble, so you're going to put more of the sodium nitrate. If you only have 100 grams of water, but you can put 110 grams of that salt in there, this is still the solute, the sodium nitrate, because when you do it, it looks like water. Okay, it's just like dissolving salt in water. It's clear. Okay, it's a clear liquid. So even though there is more, this is the solute, and so it's just that easy. You just look at the graph, look at the information given, and determine your answer. So that one's pretty straightforward. Okay, next one. I want to know how many grams of potassium iodide will dissolve in 75 grams of water at 25 degrees Celsius. So once again, we need to look at this thing. So here's our highlighter. This time, this isn't going to work because this is a different quantity, right? So we don't have the same amount of water. But honestly, it's not that difficult. All we have to do is make a proportion. Okay, and I'll show you how to do that. So we're looking at potassium iodide. That's this guy. Oops. My line got a little wonky there. I don't know what's going on. There we go, that guy. Okay. And we need 25 degrees. So that's this guy. It's a good thing it wasn't any warmer because you're going to notice that it flies off the chart at that point, right? So what we know from reading this graph is, no, we don't want calligraphy pen. We want regular pen. Okay, that it looks like it'll hold at 25 degrees Celsius. We have 150 grams of water. So we're going to, or 150 grams of potassium iodide. So it'll dissolve 150 grams of potassium iodide in 100 grams of water. Okay. You don't want to use this number 25 in our conversion because that number 25 is just something we're reading here from the graph. All right. So we're just looking at quantities. We don't want temperature in our calculation. So what we need to do is we need to make a proportion because we don't want 100 grams of water. We said we only have 75. Well, if 150 dissolve in 100, we want to know X, how many dissolve in 75 grams of water, right? And so basically what we have here is just a proportion. And so we have 4 quantities, 3 of them are known, 1 are unknown. So all we have to do is rearrange and solve for X. So to do this, what do? Well, you cross multiply. And so what happens, this ends up being, it looks like this, 75 grams of water times 150 grams of potassium iodide divided by 100 grams of water is going to give us our amount, our X. Notice we have grams of water in the numerator and the denominator of our fraction. If you have 100 or the grams of water on top and on bottom, you can cancel them. The unit you're left with is grams of potassium iodide, which is good because that's what we want to know. We want to know how many grams of potassium iodide you could dissolve in that quantity of water. Now all you have to do is solve for X. You're going to take 750 times 150 and you're going to divide by 100. When you do so, you're going to end up with 112.5 grams of potassium iodide. And that's in 75 grams of water at 25 degrees Celsius. Okay? So not that hard, it's just setting up a proportion. All right? Let's do another example. Let's say I give you something that looks like this. Okay, it says at 70 degrees Celsius, 160 grams of potassium nitrate is dissolved in 100 grams of water. Is the solution saturated, unsaturated, or supersaturated? So it's just asking, once again, if you look at this, it says 100 grams of water, so we're good here. We can just read the graph. And we're looking at potassium nitrate, which is this guy. Okay, and 70 degrees, which is right over here, so we need to find where that intersects. It looks like it intersects maybe, yep, looks like right at 130. Okay, and so we've got 160. Well, before we even did this, I could kind of tell you that it was going to be super because our graph only goes up to 100, and so, you know, when you look where it intersects, it's way below there. So simply by reading the graph and looking at the graph, we know that this is going to be a super saturated solution. Okay, because it's going to lie, you know, somewhere up here off of the graph. You know, over here, I guess. But yeah, somewhere way up here, way higher than it is. Okay, so you know, it's supersaturated solution. And now let's say I bumped, the solution, or I, stir it, or I put a little seed crystal, I drop an extra crystal in there, what's going to happen? Well, what's going to happen, okay, so if it has 160 grams, but it's only supposed to be able to hold 130, you'd have about 30 grams of this stuff precipitating out. It didn't ask that in this question, but I mean, I could ask you that. So this is about, pen's being a little weird. So about 30 grams. Grams. You get what we're talking about. 30 grams would precipitate out. PBT means precipitate, okay? But really all it was asking was this, but I could ask how much would come out of the solution. Okay, one more. Let's say I want to know how many grams of water will be needed to dissolve 25 grams of potassium nitrate in 40 degrees Celsius water. So this time we need to solve for the amount of water. So let's take a look here. Let's get out the highlighter, and so we're looking at potassium nitrate, which once again is this guy. And so we were saying it was what? 40 degrees Celsius water. Okay, it looks like it can hold maybe just over that. It looks like 61 maybe. So we know that 100 grams of water This is being goofy. I wonder what's going on. Let's see. So 100 grams of water will dissolve, we said what, roughly 61 grams? I don't know what it's doing. I don't know why it's writing that way. It's not my writing. Ugh. Come on, pen. Let's give you another shot here. Let's see. So he said 61 grams of KNO3 at 40 degrees Celsius, right? And so what we're going to do is another proportion. And guys, it doesn't have to be, you don't even have to put the grams of salt over the grams of water. You can flip it. It's the same thing. You'll notice when you solve it, you get the same answer. I always like having my x in the numerator. That way I'm not solving the inverse of x. I'll show you what I mean. So how I would go about doing this, I would put the water on top if I'm solving for the water. So I know for every 100 grams of water, there are 61 grams of potassium nitrate for that. Once again, I'm not going to put 40 in my problem because that 40 was only to read the graph, all right? And so I want to know the mass of water because I want to know how many grams of water would dissolve, let's see, 25 grams, it said. Okay, so it's basically the same thing. And what I would do is just rearrange and solve for x. So I'm going to put the 25 grams of potassium nitrate on top times 100 grams of water divided by 61 grams of potassium nitrate, and that equals x. So I'm just cross multiplying. Grams of potassium nitrate cancel. And so what do I got here? I got 2,500 divided by 61. And so that tells us that this is 40.98 grams of water. So it'd take roughly almost 41 grams of water to dissolve that amount. Okay, and so that's how I would go about doing it. If you want to flip it and do the other way, feel free. I think you'll notice that it works out the exact same. And what I mean when I say the other way, I mean this. If you want to put the salt on top, I don't know what my pen's doing. It's being goofy. If you want to put 61 grams of KNO3 on top and put 100 grams of water down below, and you want to put your 25 grams of KNO3 on top and your X grams of water below, and if you solve this, rearrange, cross multiply, divide, you're going to get the same answer. The only key is that you have to keep the grams of the salt on the same side, either being the numerator or the denominator. Same thing with the grams of the water. As long as you're consistent, it doesn't matter. you can flip that either way. It's just a conversion factor. It's just a proportion. Okay, so that's that. I'm going to give you guys some time to practice some of these. So go ahead and do so. And then afterwards, we'll go over them and share the answers. All right.